Hello and welcome back to Calculus 1, to the most important section of integration chapter, and one that will save your life, your academic life in Calculus 2 and beyond. The most important integration technique, because you rarely see basic integrals, just like you barely have to do derivative of sine x. And the reason why u substitution is the most important technique is because it is backwards chain rule. We know that out of all derivative techniques and all the derivatives you have to do, chain rule is the most frequent one. And naturally, u substitution, which is backwards chain rule, should be the most used one method of integration. Further, when you go into Calc 2, Chapter 7 is all about integration, learning new methods like integration by parts and trig substitution and all of these. Most of those techniques you learn are actually ways to convert the problem so that u sub can be done so you can finish off the problem. So I will give you first few basic examples, but I will also warn you that u sub really depends on your experience with it. There is no prescribed formula on how to do it. I did develop something that I call function derivative pair, which is like something like a technique on how to deal with this, but in a nutshell is the experience. And many times if you ask me, well, how did you know? Well, my answer is either experience or like magic, but there is no formula to it. So I will write that, let's say you have to take the integral of a square root of x plus 3 dx. You know how to take the integral of square root of x dx. But then this plus 3 is really changing that. Because you can write that x, right, as x to the 1/2, and then you integrate that and you get your x to the 3/2 over 3/2 plus c. So this is what you know. But it's x plus 3 that you have. So the trick over here is that in your head you say, let me try to set x plus 3 equal to a new variable, and we call it u. So u equals x plus 3. So now I am changing the main variable of the problem, which used to be u, x into u. But observe that we still have dx there. So I have to change dx as well. So now I'm going to say, since I am changing x into u, I have to change dx into du. And that happens by simply differentiating your substitution equation. So substitution equation is not something that you can get through a formula. Substitution depends on the problem, and it's different every time. So experience is teaching you which is the correct one. Once you have that down, you simply go and you say du over dx is equal to 1. Therefore, in this case, du equals dx, because you move dx to the other side, right? So now you have all of the pieces that you need to substitute. Your integral is still integral. Square root is a square root. X plus 3 became u, and dx became du. And you went through this change, this transformation, and you're left with the integral that you can solve easily, which is u to the 3/2 divided by 3/2 plus c. Aha. But this cannot be left as the answer, because your original problem is posed in terms of x variable in x domain. Your answer must also be those same variables. And how you do that? You plug back. So you will say 2/3 x plus 3 raised to the 3/2 plus c. And that is your answer. So it has to be in terms of the original variable. So let's recap this problem. We are starting with the integral of square root of x plus 3. And we don't know how to do that. It's not a basic integral. However, you say to yourself, well, I would be able to do it if there was only one variable under the root, which is what drives you to say, let me replace x plus 3 by one thing, one variable, call it u. So you made that choice because you wanted a single thing under, because you know how to do this. So now once you have that x plus 3 is going to be replaced by u, then all of the variables in the problem have to become in terms of u, including dx. So transformation of dx will always be done through the derivative of the substitution. And then you will get your integral in terms of variable u, which will further be calculated the same way like if it was in x. And then at the end, you will replace that new variable u with the variable that you were supposed to have in the first place, which is x plus 3. Do we all get this? Let's take a look at another case. You remember how you were asked to memorize that the integral of e to the ax dx is 1 over a e to the ax plus c? The book just said, memorize this. But as any good old 4-year-old, you should definitely ask why, right? Because that's what they do all day long. And here is why. So let's just solve the problem e to the 3x dx. I like writing number 3. It's easy to write. Much easier than 5. I don't have to lift the pen. So let me say that I know how to integrate e to the x dx, which is just e to the x plus c, right? So if I could just make this exponent to be one thing, and I can, u equals 3x. And I know I need to differentiate, so du over dx is going to be 3, from where du is 3 dx. Okay, now I have some, I can feel some disturbance in the force here, right? Because I have e to the u, right? Because this 3x is defined as u. But look at the dx. I have 3 dx. So how about I write du over 3, right? Move this 3 to the other side. So I have dx is equal to du over 3. So I solve for dx and I plug that in. It's a substitution method. You're substituting things. So now this integral becomes 1/3 integral of e to the u du, which, dare I say clearly, is 1/3 e to the u plus c. And then don't forget to go back into original variable, okay? You can use the sentence, I don't care about u, I care about the x. No, yeah, because you don't want u back, right? X is the main variable. So I don't care about u, I care about the x. Makes sense.
Makes sense. Things that you never want to hear outside of Calc class.
Oh yeah, not to be. Oh.
Single K down the G.
Okay. So now do we see how that 3 magically goes all the way and becomes 1/3 in front? Right? It is this process of u substitution and that shoveling over there with du dx that brings it out. So if it works for e, it better work for sine, cosine, and all of the other ones. So I would like to challenge you with figuring out integral of cosine of, I don't know, 8x dx, right? And I'm telling you that the steps are going to be identical to what you had for e. So get that 1/8 sine using the same method.
How come the first one?
Isn't that
How come on the first one you didn't change e to any value?
because you didn't write it down. So you don't know. Not for you. You was a dx, which is 1. And then du was equal to dx, which is equal to.
Which is fine because
Well, here, zero. Now, here. Well, you didn't write the most important thing.
e to c.
Yeah, I know, but the most important thing is that du is equal to 3. Because of the first one. And then you move to the side. So in previous column, du over dx. Why? Because du is equal to 3 dx. Right? I gotta fix that.
Oh yes, I'm looking at the outside.
So you play for fun from last quarter.
No, 3. Much more than. It's not the money.
I know that's crazy.
So we are going to use the same technique. U is equal to 8x, because you know how to integrate cosine of x, so cosine of u. And then du is 8 dx, right? When you differentiate, you can put dx immediately on the other side. And then from there, you realize that dx is du over 8. I will show you another way to deal with this. So now you have integral cosine of 8x becomes cosine of u, and then we have du over 8, which is equal to 1 over 8 in front of the integral cosine u du, which is 1 over 8 sine u plus c, and then I don't care about u, care about the x, which is sine 8x plus c. All good? Now, I would like to do the same problem, integral cosine 8x dx, but I'm going to switch it just a tiny bit, okay? First of all, I want to emphasize one more time that there is a multiplication symbol in between the function f of x and dx. There is multiplication there. And the dx is actually the width. So height times the width to get the area of the rectangle. Now that is going to be important because when I do substitution now, look what happens. We started the same way. What I'm going to ask you guys is to pick method 1 or method 2. There's no reason to force both. If you like one better than the other, that's the one you're going to use. I care about the correct answer at the end. I can't care less which method you use. So here's the other way. So previous way was you figure out what substitution is, you differentiate, and then you make dx equals everything else, and then you plug that in. That was the old way. Now here's the new way. The new way says, here's the same substitution, here's the same derivative. Obviously that can't change. But now when you start substituting, you go, okay, that's cosine u, but then you only have a dx and you need 8 dx. So what you are going to do is you are going to fix that by placing an 8 and 1 over 8 to balance it out in front. Because 1/8 times 8 is 1. So why are you doing this? Because you need that 8. So you see that now that 1/8 will copy and the 8 dx will be du. So you are technically fixing it, right, by multiplying by 8, which you needed for the substitution, and then balancing that out between with 1/8 in front. Leads to the same conclusion, which is 1 over 8 sine u plus c, which is 1 over 8 sine 8x plus c. It looks much cleaner, looks much faster, but again, it might be easier for you, but again, you can use the other method. Whatever works better for you. I think that the first method is more structured in terms of you're just plugging things in. You don't have to think of how to fix the problem that it's missing stuff. But this one has its value, points as well. Now, the most important thing to realize here is that you can only fix constants this way. You cannot fix if you're missing an x or cosine x. So only constants can be fixed this way. I'm going to write it in blood. I don't want any issues with you coming up with x and then 1 over x in front. That would be terribly wrong. You can only fix numbers this way, constants. Because constants are free to go in and out of the integral. X's are not. All right. So the next problem would be, say you are challenged with a task to integrate 2x plus 5 squared dx. You say that's easy. All I need to do is to FOIL 2x plus 5 times 2x plus 5, integrate each term, and you're done in 5 seconds, right? And I said, oh yeah, I didn't think about that. Let's make this to 207 then, FOIL now. Which is, you would obviously say, sure, not a problem, right? And then in the 2 years, you'll have the answer for that, right? So, as you can see, problems can be as annoying as we want them to be. And as much as you can do this by algebra, because foiling, 206 times would be insane, I would say, well, you know what I know? I know how much x to the 207 is. Just, it's not an issue at all, right? You just add 1 and you're done. So let me make whatever is inside the parenthesis, that one thing, call it u equals 2x plus 5. And then clearly du is 2dx when you take the derivative. Do I have 2dx? No. So I fix that by putting in the constant in there. And now I can do the substitution. 1/2 integral. I have u to the 207. And then 2dx gives me du. Which further becomes 1/2 u to the 208 divided by 208 plus c. And then at the end, right, I don't care about u, care about the x, which is 1 over 416 2x plus 5 to the 208 plus c, which is the answer. That's how you do these problems. Those are the introductory ones. Now we're going to take a look at spicier situations. What happens if you are to integrate 2x sine x squared dx? All right. Now I'm looking at a problem that has a linear function 2x as a function, sine of something as a function, x squared as a function. So I have a whole bunch of functions and possibilities in this problem. My suggestion on how to battle and navigate these more difficult problems is to look for function derivative pair. So function derivative pair. What does this mean? Well, in the problem, in order for it to be doable by use substitution, you must have function and its derivative present. Do I have the derivative of sine present in this problem? No, I don't, right? So sine cannot be part of function. Now function is related to u and the derivative is related to du. So the way this is, I developed this way of thinking over years to kind of try and help you figure out quicker what is the valid u, and then du is the derivative, and then so on. So function derivative pair will help you pick correct u. If there is no derivative present in the problem, whatever you picked cannot be u, because you have to differentiate it. So you are always looking for function derivative pair, and whatever ends up being the function, the other thing is the derivative of it, which is du. So looking at this, I have, if I pick x squared as a function, there is the 2x, which is its derivative. So x squared is correct u to be picked for this particular problem. So I will pick u as x squared, because its derivative is also present. And then you would say, well, what am I doing with a sign? Well, substitute and check. I have a string of 2x dx. All of that is du. So if you carefully look at this integral, this changes into sine u du, which is easy, right? So we went from something that cannot be done with basic integrals into something that is a joke. It's a basic integral. And you see that that sine just stay there, but it's okay. You can integrate sine. So you don't have to substitute everything, right? Certain things can stay. Just like we had an example with our e earlier. Right? I used this exponent only, and e stayed, so it was e to the u. Cosines and sines stayed. So now integral of this is negative cosine u plus c, and then negative cosine of x squared plus c. Yes.
What happened to you?
It's right here. What do you mean what happened to it? When you integrate, there's no more dx du. You put plus c and you move on, right? Okay. Now, why is integration so awesome? We can check it every time. So if you're not lazy, the derivative of negative cosine x squared plus c is equal to, copy the negative, I can put negative 1, and now integral of cosine is negative sine x squared. The chain rule from here will give me 2x, and then derivative of c is 0. It doesn't take a nuclear physics degree to see that this is actually 2x sine squared x squared, right? Negatives will cancel, plus 0 drop, and you have the original problem. So if you're not lazy and you care, you will simply integrate, differentiate at the end quickly to show that the problem is right. What now? What happened? What? Break up? What do you mean break up?
Sorry, Nick, it's just not right now. I don't care about you, I care about you.
I see how it is. Nice. Never heard of that.
The Snapchat filter for a wall has bricks in it though. I don't get it. People like the Snapchat filter for brick craft or something.
But walls are made out of bricks, unless they're made out of plastic or something. Okay with that in a certain area.
Can I just
You
put this
just
right
make it
here?
up for like an invisible thing. You just have to put like dot collars on everybody and then we'll know.
You know what you do? You have like automated turrets and then
Yes,
the lines.
Like in what was that one?
How about we take a look at the problem and look for function derivative pair?
I suppose. How about
How about, what's the function? Sine x, yes. So if I have a function derivative pair, if I put sine x here, then its derivative is cosine x. Good. That helps me because I know u is equal to sine x. and then du is cosine x dx. And then you probably go, but what do I do with the 8? 8 is the exponent. So I can just write it this way. If you know your trig well, you know you would be able to write it this way, right? So it becomes, as you said, u to the 8. I will still underline du part twice to make sure that you see that it's the same. So that mess goes together. Entire cosine x dx becomes du as the replacement. So the answer is 1 over 9 u to the 9 plus c, which is actually 1 over 9 sine to the 9 x plus c as the answer we present. How often is this used? Every single problem in Calc 2. That's how often it's used. And this is, the good thing about this is I get to jump between these. So trig integrals, and as you can see, this is me teaching Calc 2. I give you all the basics, which is what we reviewed earlier today. Talked about pairing, and then look at that. U substitution is the first problem you do. U substitution, once you break this apart, is the second. It's written in the margin, on a side. But this problem over here has sine to the 8 cosine cubed, and then we are learning how to peel off one cosine to leave it for du, and then the rest of the cosines get transformed into sines, and then distributed cosine creates two separate integrals, which each one is solved with the u substitution to get this. Every single problem. Here's the u sub again. The next problem will have u sub again. The next problem will have u sub in every single problem.
This is Calc 2, right?
Calc 2, yeah.
I would say these are some pretty difficult.
Well, look, it's one step at a time. So you're looking at the chapter 7.3, right?
Yeah, you can do it.
Of course you can. It's not difficult. It's just that, if you miss this step in your building block, I'm telling you that 7.3 is impossible, because every problem is using what we are learning now to finish it off. Because 7.3, as you see, is a marriage between you knowing trig identities in this part and knowing u sub to do the actual integral at the end, which is what makes Calc 2 distinguished, should I say. Because in this one problem, we used trig identity to transform, we used algebra to distribute stuff, we used Calc 1 that you can split integrals, and then we used u sub to actually solve it. And most of the problems of Calc 2 assume all of that knowledge from before. So at the end of this course, obviously, next Saturday, I will spell out all of the things that you absolutely must practice over the summer, or if you're taking it in the summer, Calc 2, within those 2 weeks. What trig identities and things you need to survive Calc 2. Otherwise, it's just doom. Yes?
Why does U substitution remind me of something from like algebra 2?
Yeah, I was thinking that as well.
There's like another, the substitutions I remember doing before calculus, like long before calculus.
The only substitution that I can think from algebra is the problems that look like quadratics and can be transformed into quadratics. But it also appeared in your pre-calculus one when you did exponential equation. So if you had a problem in algebra that looked like this, plus 5x to the 1/3 plus 6 equal to 0, this was your algebra 2 problem, and you used to say u equals x to the 1/3, or you use a different letter, which turns it into u squared plus 5u plus 6 equal to 0, and then it's easy after that.
Oh, right.
That was algebra, and then there was another one in your pre-calculus 1 class, which had the same thing, e to the 2x plus, let's say, 2e to the x plus 1 equal to 0, where you said u equals e to the x, and then you were getting your u squared plus 2u plus 1 equal to 0, right? So these transformations are there. It's just, actually it would be better if I put -3 over here, because then at least we can solve something over here. So this is pre-calc 1, PC1. So you have seen these substitutions before, but we didn't make a big deal out of them because, you know, some people see that they can factor without actually using u sub. But now in integration, you just have no other choice. You are stuck with it. You have to use it.
I just think it's like really cool that like all of the foundational. I mean, like you could ultimately like derive the integrals from the derivative initially.
Yeah.
It's like it's all just going back to stuff we learned a long time ago.
Well, mathematics always builds up on the previous concept. You never start from scratch, which is why a lot of people actually fall off the truck in the math education, because they said, okay, if I miss this one lecture, you know, not a big deal. Well, when you miss one lecture and you learn a concept in math, you shut the door to a completely, like, whole branches of mathematics, because there is I remember at NGIT, there was this one professor who was notorious for it, that he starts the class on time every day. Like, so if the class starts at 11 a.m., 11:00, he's ready with a chalk. At 11:00, he starts writing definition. If you walk in after he explained that definition, you're kicked out, because the day is just gone. You missed the definition, and you have no clue what the rest of the class is going to be about, and most likely you just mathematically are done. So I know. So that is true. So you see these, you know, substitutions. This is the same concept, except we didn't have to take derivatives here, because there was no dx part to these problems. But the u part is identical. So now we are upgrading this, where you have to have your u sub portion, and then because you have to replace dx as well, you would go and say du equals, and you take the derivative, right, x to the negative 2/3, and then dx, and then, right, plug that in as well. So it builds up. It builds up. All right, so now I'm going to take a look at problems from the textbook. But before we do that, and we will do the definite integrals also with substitution. But before we do that, I just want to recap real quick what we did so far. So first few examples were all about basic substitution, where we had to fix a constant at most. So we were trying to learn what would be the correct choice for u, and then du would be set in stone as soon as you pick u. Du is set because it's just its derivative. If it's not working, if you are getting the worse integral after you do the substitution, obviously you made the wrong choice. You will have to reevaluate. We've seen e to the 3x, we've seen cosine to the 8x, so all of these problems are done the same way. And then we've seen this one, where you had this binomial 2x plus 5 raised to the 207th power, right? Which you don't want to FOIL. But then we move into spicier problems, which involve multiplication of functions. And it is this where you use this function derivative kind of idea to try and figure out what appropriate u would be. Because as you can see, you can put u to be 2x, you can put u to be x squared, you can put u to be sine of x squared. You can put any of those to be u. But only one of them is a right choice, and the other ones will make the problem impossible to do. And the trick is to look for a function derivative pair, keeping an open mind that you can always fix constants. So even if this problem was just x sine x squared, I would still use the same x squared, because that 2 that was missing, I could just put 2 and 1/2 in front, and I would still be able to solve the problem. Another one that utilizes trig, but this time u was sine x, not just the argument, but the entire function, because its derivative cosine is present. Now, it's worth mentioning here that we understand that the derivative of sine is cosine, derivative of cosine is sine. But we cannot use u equal cosine, because you don't have only one sine for du. You see, that's the little trick that you have to be careful here. You have 8 sines. So if you pick cosine as u, you will get one sine to be used as du, and you still have 7 sines floating around with nothing to sub it for, which is a problem. So when you have situations like this, you're always trying to put u to be something that had exponent on it, or it's in the root, or it's, you know, trapped in some way, to make that simple. And that's exactly what it did. As you can see, sine to the 8 became u to the 8. Why did I say u? That's in Serbian, u. Yeah, u. Anyway, so there we have it, sine to the 8. Now, I mean, let me just write. I'm going to write on the board and just think about this. So you can see it, sine x cosine x dx. For this particular problem, it doesn't matter which one you pick. So if there are no exponents, if it's just sine x cosine x, it doesn't matter which one you pick for you, because the other one is present, right? But over there in our problem that we are looking at, sine to the 8, you must pick sine, because you have a single cosine for du. If you pick cosine, well, you will have one sine used up for du, and then you will still have 7 sines just hanging around. Now, obviously, hopefully you will, you know, once you go home, for some of you tomorrow, you will hopefully do this problem 2 ways. And then you will say, but wait, don't I get a minus sign if I do it one way, and then the positive if I do it other way, and how they can be the same? It will be clear once you actually do it. It will be clear. Yes?
Is it because of the period and amplitude?
No. Nope. When you do it, you'll see it. But the answer to that is no. And now, we are going to take a look at a few examples from the textbook, so that we are all on the same page. So here is number 18, one of my favorites. Frequently I had this one on exams. Have you found function derivative pair?
Uh-huh.
What is it?
U is x squared.
Yes. Function derivative pair is x squared and then x. So u is x squared, du is 2x dx. I don't have the 2, so I will fix that. Becomes 1/2 integral e to the u du, which is 1/2 e to the u plus c, which is 1/2 e to the x squared plus c. Problem solved. That was problem 18. Spicier example, problem 20. Integral of the square root of x plus 1, everything raised to the 4th power, divided by 2 root x dx.
Wait, can you just do the first one as well then?
What happened?
That's a stupid question. Could you just go for 18? Like, there's no stupid questions here. No, there are. Only stupid people.
Nope, no super question. So here we go. The function derivative pair was x squared and its derivative is x.
Right.
So we pick x squared because that was the function to be the,
Oh, du is just 2x dx.
yes.
Just add in the dx.
I have x dx, I needed the 2. Right? To match the 2.
Mm-hmm.
So I put in the 2.5 to balance it.
So you just rewrite.
Mm-hmm.
And then the half comes from,
Balancing the 2.
so it cancels because you added the 2?
Yes.
Okay. And that goes just outside the integral itself.
Yeah. Because constants can escape integration. That, which is the reason why you're not allowed to do that with x's. You can only do it with constants.
So why don't you just, but you can't do it with coefficients?
But that is the coefficient too. It's called also coefficient. Constant coefficient.
Well, right. So, I mean, why doesn't,
It doesn't work for x.
but they just,
So this problem had x to begin with, so we were able to use u sub. If you have a problem just like this, and now you have to fudge 2x, you can't. You can't, because you can't put
right.
x
So
out of
in that
nowhere.
case, you would just integrate into the x squared
Yeah, but you can't.
at all.
Yep, nope. Well, there are methods through Calc 3, there are methods through, there even in Calc 2 there is something that you can do which is really cool. Complex variables also, but nothing you can do in Calc 1 and nothing you can do in Calc 2 all the way to chapter 9.
So you put the 2 in, and then to balance the 2, you have the half outside.
Yes.
Okay.
So what do I do for the problem below? Think about it for a second.
Is that a 4?
Yeah, that's a 4. Better?
No, I like my 4s with triangles on top. That's how I used to write them until in 5th grade. My teacher said I couldn't do it anymore because there was in a class that, like, they had issues like writing 9s or something like that. Like, my 4s looked like their 9s because they couldn't write.
I see.
I don't know.
Also the flag looks the same way,
Yeah.
but on the other side. All right. So what should I pick here as U?
Square root of x plus 1.
Very good. And then I'm gonna leave you to your own devices to work it out a little bit.
So you just stick out the fun part.
That is the only fun, difficult part. The rest is a grind. So, let's see.
Man.
Everyone done? All right, so I like to, let me draw a peanut there. So this peanut, the whole peanut is du. So I have u to the 4 du. So entire problem that was really looking bad to begin with becomes just 1/5 u to the 5 plus c, which is, I can write it, root x plus 1 over 5, oh, everything to the 5 over 5 plus c. That was problem 20. Let's see what else spicy we can find. We don't have per se anything spicy here.
What if you throw a log in there?
Alright.
That's a really good log.
Yeah, it is a good log.
I gotta
But
say,
it's like the log that you can substitution. That's the point.
It has a handle. So here, I throw in a log. Sounds good?
Yeah.
Alright, next problem.
Do you solve
Wait,
that one with
yeah,
the
what-
timing, or
what happens when you integrate that log? Does it become a tree?
It's calc 2.
do you solve that with like the hand sign on, or
So it's gonna be calc 2. Fair?
But if you integrate a piece of wood, you get a tree.
No. You can integrate piece of wood in a piece of furniture, right? And yeah.
Is that what C is?
Yeah. So eventually
C is the whole.
you get this. Alright, but let's just move on with let's move on with calc 1. The log questions will be in calc 2. Fair?
oh, see?
Yeah.
Oh, yeah.
That's what he's trying to say.
You don't listen to much. I thought we were just being hard.
Thought we were.
I would definitely not be teaching that one. I'm good with stick figures.
If you teach number systems, you do, right?
Yeah, sometimes.
Okay. Do you know what you're teaching next semester yet?
Over the summer, I'm doing 2 calc 1s, calc 2, and calc 3.
Mm-hmm.
The next semester, I'm doing definitely calc 1, calc 2 in the fall. Calc 1, calc 2, and so far, algebra and 3 calc 1. So far. But I do have another hole for another class, so if there is a need for calc 3 class, or differential equations, if not, then maybe another algebra, maybe, I don't know, there's possibilities there. Seems to me you're picking up some kind of Lego course.
Yeah?
Yeah, I do
I'll take Lego first.
Lego robotics. Yeah, you should start like a BattleBots club.
yeah.
I think we have that, actually.
Robotics is robotics club. I know there's like engineering.
What's the function of the pair here?
I know. Actually, like
X to the 10 and x to the
actually like
10x to the 9. Good. Let's see what you get.
just plus C all the time because C could be 0. So you get like different clouds.
No, stop it. Add the plus C. And then you can compute it.
Does 0 have a big word?
Yeah.
Always?
Oh.
4 has a big word as well. Maybe that's just something over there. Let's do 1 episode.
How do you feel? Is that what you call that? No, I appreciate it.
Charlie? What?
No.
Charlie's a good guy.
Have you ever met a Charlie?
Yeah, I know Charlie.
I know Charlie. I know two Charlie.
I don't think I know any Charlie.
Oh, you're unfortunate.
Maybe that's why
You missed out in life.
I think about just C's. I have no Charlies to relate to.
It's so much easier though, because like you know, like you can't forget Charlie. Like first thing.
No, I could forget Charlie.
Yeah.
Do not forget people, Alex. Let's say.
Maybe if you work with like Christine or something, then maybe it will work for you.
You mean a girl Charlie?
Yeah.
Well, my brother's trying how to change it for him. I did it all.
Yeah, she's gonna keep that name until she can legally change it on her
Yeah,
own.
that's what I'm
No,
saying.
but like it's like a thing now.
Charlie.
Yeah.
It's like a thing now.
Yeah.
At least we're past. Wait, we're past. Like,
When you
the
can you please
actors.
stand up?
Charlie
Just
the
for a
girl
second.
in the chocolate factory.
Right. All right. So if I say Charlie, you
Yes.
can kind of Charlie, like kind of a little bit. Can you please stand up? How's this gonna be Charlie?
Yeah.
There's no way.
Well, like they her name's Charlotte, but they call her
Yeah.
Charlie.
What? Her name's Charlie, they call her Charlie?
No.
Her name's Charlie.
Oh,
so they call
Charlotte.
her
But they call her Charlotte, like that's it.
Even worse. All right.
Charlie.
Charlotte. And that's when they call her
Charlotte.
That's like the
I
worst
hate
name
that
I've ever-
so much. That's like how Margaret is
I have the best
Peggy,
name.
right? And Margaret's such a beautiful name.
I know.
Peggy sounds
Margaret
like
is an
something
amazing
that you
name.
would name a pig, right?
I know a person. I know a person with Margaret, and I love that name.
Yeah, man.
And then Peggy.
Dude, if anyone.
And you know what it reminds me of? The commercial. Hi, my name Peggy.
If my name was Margaret and anyone ever called me
Okay, how does
Peggy, I would
Margaret
kill.
relate to Peggy?
I don't know. It just-
That is mystery to us all.
Charlie.
But I know a person.
That's like
No.
Richard and Dick.
Yeah.
Yeah.
But
No, I
But still,
would
there
name
is
my
D there.
daughter,
Huh?
what was it?
it has a D in it.
Yeah.
Yeah, I would name her
There's
Charlotte.
nothing
I
I
wouldn't
think
name her
no, but I think
Charlie.
that's so like Charlie. I think it's like I think it's cute. Like, that was
Yeah, keep talking.
Is it
I'm just going to
Margaret?
solve this. You already
No.
did this on the board. You don't know how to do it.
No, what was the name?
Integral of x
Margaret.
squared.
Or Peggy.
So I need 10, 1 over 10
call
in
it
front,
Mark.
x to the 9, sine x to the 10 dx is 1 over 10 integral sine u du, which is 1 over 10 negative cosine u plus c, which is negative 1 over 10 cosine of x to the 10 plus c. And what else? Ah, yes, let's not forget. Never forget to do definite integrals. You're gonna love these. definite integrals with u sub. Okay. Here is the most important thing that you have to realize. Integral a to b of f of x dx is eventually equal to f of x computed from a to b, which is f of b minus f of a. I know I wrote this like 5,000 times. The most important part for you to realize is that the limits are also x's, because the associated graph, when this represents area under the curve, if you see this, both a and b are on x-axis. You can think of them as x1 and x2. The function is f of x, and then you have dx. So guys, when you are transforming the integral using u sub, that it's a definite integral, you have to transform limits of integration as well. Because if you have integral that goes from x1 to x2 f of x dx, and you change that into g of u du, you better have u1 and u2. Limits change with u sub. Let me exaggerate on that one a little bit. Limits change with u sub. You cannot plug x limits. Let's say the integral was 0 to 1 and then blah blah, and you did u sub. Those 0 to 1 were x values, but now your integrals in terms of u. You have to change those limits in the u domain. So let's take a look at the problem. Say I have integral from -1 to 2 x squared e to the x cubed plus 1 dx. Well, you clearly see the substitution here. What's the substitution? Yes, x cubed plus 1. And what do I get for du? Dx. So I need to fix that 3 and the 1/3 in front, and I can go with 1/3 integral e to the u du. And now, limits. The old limit x1 was -1. When you feed that into the u equation, you get -1 cubed plus 1, and you get 0. So bottom limit changes from -1 to 0. And you're just using your u substitution to solve it.
So we don't have to change the 5 to x.
Exactly.
Okay.
So you just now have x2, which is 2. So u is equal to 2 cubed plus 1, which is 9. The top limit changes into 9. So please understand this right away, that -1 and 2 are x limits for x function. 0 and 9 are u limits for u function. Transformation is as simple as just plugging those x's into u substitution and dealing with that quickly. So nothing spectacular is happening there. So now you know how to deal with this. It's e to the 1/3 e to the u from 0 to 9, which is 1/3 e to the 9 minus 1. No plus c, it's a definite integral. Oh, I forgot the parentheses. Holy nightmare. That 1/3 has to distribute to everything. I mean, you could write it as e to the 9 minus 1 everything over 3. Whatever makes you smile. That's most important. Smile is important. Anyone? All right, 1, 2, 3, 4. Come on. Come on. 5. There it is. Yeah. Awesome. Thank you, for being on board. Do you think we can transform those ugly sine and cosine pi over 2 and pi over 3 limits into values that we could use? Yeah, we can. Yes, we can. But they have few interesting things. So here, try this one. It looks so bad. V squared plus 1 divided by the square root of v cubed plus 3v plus 4 actually there's no, yeah, okay, good. And then dv, and it goes from 0 to 3. It's awesome. Figure out function derivative pair, play with it a little bit. Check my partial point.
Judge that. Instead, just stay home and stream and put the stream up over here. And
Yeah. You never had sick days.
that's true. No, I can. what is u?
V to the third plus 3v plus 4.
Let's take a look at this together. So I see v cubed and then v squared, so that should be good for sub. U equals v cubed plus 3v plus 4, which means that the du is going to be 3v squared plus 3, all of that in parentheses, dv. And if I factor out 3, I have v squared plus 1, which is exactly what I have on top. So v squared and dv. So I know I need to multiply by 3. I need to multiply by 3. And 1/3 in front to balance it out. So the whole thing becomes 1/3 integral. I have du divided by the square root of u. And now I have to transform the limits. Plug in 0. Limits. So when v is equal to 0, u is going to be 0 cubed plus 3 times 0 plus 4. So it's equal to 4. So lower limit is 4. And when v is equal to 3, we get that u is 3 cubed plus 3 times 3 plus 4. So that's 27 plus 9 is 36 plus 4 is 40. So the limits change from 0 to 3 to 4 to 40. So this is now 1/3 integral 4 to 40 of u to the negative 1/2 du, which is 1/3 u to the 1/2 over 1/2, which is just going to give us 2 on top, computed from 4 to 40, which is 2/3 root 40 minus root 4, which you can compute further, which is 2 root 10 minus 2. You can factor out 2, get 4/3 root 10 minus 1. This is exact answer. Now I know how much you love and appreciate trig, so I would not deprive you from that experience, pleasure.
No experience.
But I'm really interested in the integral of tangent x dx from pi over 4 to pi over 3. How would you solve this? We have to integrate and then plug in.
Yeah.
So how do you integrate? What's integral of tangent? That one. Very good. So you rewrite this as sine x over cosine x dx, and then you have to use u sub.
Or it doesn't matter.
No, it does.
Matters,
You can't have du on in the denominator. So this would be the last problem, then we're going to take the break, and after that review for the exam. So what's u in this case? Cosine x. You must use cosine x.
So we would be one.
Yes, because look what happens. Let's make a wrong choice and then erase it. Let's make a wrong choice to see what happens. U equals sine x and then du equals cosine x dx. Do you see how cosine is in the denominator but it's in the numerator in our substitution? It doesn't fit. It doesn't fit. That's the problem. So you see over here that it's cosine times dx, but in the problem you have dx over cosine x. They're not the same, which is the reason why you can't pick sine. So you know what, even if you make a mistake with choosing it, once you start substituting, you see it doesn't work, right? You run into a brick wall, turn around, run the other way, if you didn't get knocked out though. So you see that in the baseball, right? They run into a brick wall.
No, no one here watches baseball.
Thank you.
Baseball's boring.
That's like plus 10 on your next test.
Dude, that's
You ever-
like
have you
our
ever seen the
entire
Bros?
town. It's like
Have
this.
you ever watched the Bros?
No.
That's
We
fun.
have like 6 baseball fields.
I went to a baseball game once. It was some kind of function.
I can give a gift.
No, I actually, because there was a lot of cool and cool people there.
Yeah, that's the one plus. Like, they got
So,
some
but
pretty
I went and I tried to watch the game for like 19 seconds and it was painful.
Yeah. I've actually seen the one worse thing that's worse than watching baseball.
What?
My dad took me to the drag races over the summer. Yeah. No.
pretty bad.
Unless I think I would do any sport if I'm in it, but watching it, it's like watching the paint dry. Because I have no,
You watch Counter Strike?
Yeah. I do watch competitive gaming online, yeah. But sports, I can't. There's no way. Because I don't care about those people who play it. I don't have, people get all rounded up with like, okay, because they want their team to win. I just can't care about any of those teams. So
I feel like they get
there's like, oh my God, the tennis player from your country won.
Oh.
I was like,
they get paid
I don't
much
care.
to lose too much of the time.
Yeah.
For the six-figure salaries, I figured the athletes shouldn't really be losing any game.
But then you
Someone
go
has
against
to
other.
lose, though.
Someone has to lose so someone can win.
But like, so only the winning teams get the six-figure salaries. That's a little.
Shouldn't the losers just not make money because that's how the real world works?
No, because committed. It's all about ticket sales. It's not about. It's not about how.
Well, right. Is that like the entire premise?
No, because
Like
some
wrestling.
some things just suck.
Yeah.
No, some.
Can you help me with these limits real quick and
Yeah.
then, so u1 would be a cosine of pi over 4.
I over 4, that's
Very good.
2 over 2.
And how about cosine of pi over 3?
Cosine of pi over 3 is not on.
All right, thank you. Because for the moment there I couldn't do it. Now what is the integral of du over u? Hmm. What's the integral of?
It's usually -1, so times the
So what's the integral? We talked about it. There's your
Oh,
log.
God. Absolute value. Pose.
No plus c. These are numbers, right?
Mm-hmm.
Now you can bring them together as 1/2 divided by root 2 over 2, which is ln of these guys cancel, so you get 1 over root 2, which eventually is root 2 over 2. That's positive value, so you don't need the absolute value anyway. There you go. Which could further be written if you need it for whatever's, right? ln 2. Oh, actually you can really compress this. Look at this. God, I love these ln's. It's called the boss mode now. Right, you factor out ln 2. And you're left with 1/2 minus 1, which is negative 1/2 ln 2. I mean, we were happy here, but
Why not be even more happy?
yeah, exactly. Why not be extraordinary if you can, right? So that's it for the U sub. We will do about 10-15 problems next class after the exam for U sub, because that is the most important technique, including switching the limits of integration. So we're going to make like 5-10 minute break now, and then after that we're going to do the review. So I'll restart the stream for that one for the exam next week. Bye stream.